concept I want to begin with in introducing theoretical computer science is the idea of limitations on the power of computing. So let's see where we are. So for programmers, regular expressions are really a powerful pattern matching tool. We have a paradigm based on the theory that really facilitates the implementation, and the combination of the two are very important in the real world. For theoreticians, there's the idea that we have two different ways to describe sets of strings, and we know they're equivalent, but it's interesting to think about, are there sets of strings, are there languages and machines that can describe sets of strings that we can't do with REs and DFAs? I alluded to the fact that there are, but what are they? How do we address the idea of characterizing those types of languages in machines? Certainly the DFA is an extremely simple machine, and we imagine there must be machines that are more powerful in the terms of having the ability to describe a broader class of sets of strings, but what are those machines like? For you, as we mentioned, you've got the core principles of computer science introduced, the basic idea of abstract machines and languages, and we're going to use those things to get started on really addressing fundamental questions in theoretical computer science. So here's the basic idea. So are there sets of strings that can't be described by any regular expression? And the answer is yes, there are. And we're going to do an actual mathematical proof that shows that you can't have an RE that describes the bit strings with equal numbers of zeros and ones. And that's just one example. There's many other examples. Strings that represent legal regular expressions. There's no regular expression for describing those. Or prime numbers, or another example from biology, a complemented palindrome or palindromes. There's a long list of sets of strings that we'd like to work with that regular expressions are not powerful enough to describe. And you might say the same thing about DFAs. Are there sets of strings that can't be described by any DFAs? And of course, by Kleene's theorem, that's the same question. You can't build a deterministic finite automaton to recognize, say, bit strings with equal numbers of zeros and ones. And if you prove that, then you've proved that you can't have a regular expression that specifies that language. So that's a basic question, and let's first be sure that we have a good answer to that first question. Why is it that we say that deterministic finite automata are not sufficiently powerful to do what we want? We have a limit on the power of these abstractions. So our proposition is there exists a set of strings that can't be described by any RE or DFA. And we're going to actually do a proof. We try not to do too many proofs in this course, but a couple of them are really important. And this one you'll be able to understand. So what we're going to do is prove this by showing that for this specific language, the set of bit strings with equal number of zeros and ones, no DFA can recognize that set. So our proof is going to be by contradiction. So let's assume that we do have such a DFA. It's a finite automaton, so that means the number of states is finite, so we can just say there's a number n, which is the number of states. So that's our first thing. Let's assume that we can do that. So, it's supposed to recognize strings with equal number of zeros and ones, so it's going to recognize the string that has n plus 1 zeros followed by n plus 1 ones. So for 10, so we give it 11 zeros and 11 ones, and it's going to go ahead and recognize that. So we don't know what sequence of states that it goes through, but it's going to go through some sequence of its states. It doesn't matter what it is. As it reads each zero, it's going to, whatever complex construction it is, it's going to go to some state. And each time it's completely defined what state it goes to next. Whatever state it's in, follow the zero transition out. Now the critical thing is that since there's only n states, and we have n+1 zeros, some state's going to get revisited. There's not enough different possibilities to get through that without having some state getting revisited. But that's crucial because what happens next only depends on being in that state. So what that means is if you take the zeros between the visits of that state, the machine can't tell the difference. It's going to, whatever it does on that string with equal numbers of zeros and ones, it's going to do on this other string. It's going to start out 0, 3, 5, and once we're in position 5, it's going to do precisely the same thing for those two strings. So there's a string with equal numbers of zeros and ones that it may recognize, but there's another one that has fewer zeros than ones that it's going to recognize too. That string does not have equal number of zeros and ones, and that's a proof by contradiction. It's recognizing a string that we said it didn't recognize, so the assumption that we started with, that such a DFA exists, must be false. That's a proof that there's a set of strings, and a pretty simple one, that can't be described by any DFA or regular expression. So that's a first result in theoretical computer science. There's a limit on what we can do with this kind of machine. So it's a natural question to ask is, so is there a more powerful machine? Like, for example, is there one that can recognize this language, equal numbers of zeros and ones? And the answer is yes. What we can do is add a stack to the deterministic finite automaton. I won't give the details, but I'll give a demo and you can understand how this machine works. So with this machine, you get to, if you want, in a state, put the character that you just read on a stack. So let's look at how that one works in this example. So we read a 0, we put it on the stack. Read another 0, put it on the stack. When we read a 1 and we have 0 on the stack, we pop. But if the stack's empty, we put the 1s on. And now you can see that whichever character has appeared more is going to be on the stack, and it essentially counts the imbalance between the zeros and the ones. And if the stack is empty and we get to the end, then it lights the yes. So that's a more powerful machine that can recognize this other language. It's interesting that just by adding a stack to a DFA, we can make it recognize more larger language. There's also a formal language more complicated than regular expressions that defines the same set of strings. There's a duality between machines and languages, but we're going to focus on machines just for now. So what about more powerful than a one-stack DFA? Yeah, actually, there's languages out there that if we add a second stack, we can recognize prime numbers, we can recognize strings that are legal Java programs, many other things. And again, won't do the details of that just now. That's really about the next lecture. This is the way a theoretician thinks. I've got the simplest machine I could possibly imagine. And if I add a stack, I can do more than with the simplest one. If I add a second stack, I can do even more. And the question is, where does it stop? So we'll talk about this one next lecture. But the thing is there a machine that's got more power than a two-stack DFA? Can we add a third stack and then recognize even more languages? And the amazing answer is that no. Not even a room full of supercomputers is more powerful in this sense than a two-stack DFA. That simple abstract machine, from this standpoint, is equivalent to a room full of supercomputers. It's a basic limitation on computation that we're going to talk about in the next lecture.